Right, so I push ahead. Sometimes I like to push ahead and then I stop and we digest it, you know. So, I'm pushing ahead into 1.3 and we're going to specifically learn now about linear functions. I mean, what we did last time was we kind of got used to the idea of what's a function, and then we kind of took a look at several kinds of functions in a way, but now in the rest of this course, we specifically look at several kinds of functions in detail. So we start with linear functions. And so watch this. I'm just going to write a few things on the board here. Okay, so actually I've got a mess here. All across that board, I guess I got 5 functions. Are they all functions? I think they are all functions. Those are, you might not know all that yet. We did learn about functions, but staring at an equation, it's rather hard to tell whether it's a function, but I'll just spill the beans. These are all functions. That's not my point. My point is now which ones are linear? Which one of these are lines? Which ones of these are linear? Can you tell me which ones of these are linear? And which ones are not linear, I guess? That's what I'd like to know. And maybe I haven't really told you, although maybe I said something last week that you recall, or maybe you already know. Any ideas? This one?
Yes.
Yes, that's linear. Yeah, classic linear function. I think the idea is this. Both variables are to the first power. That's my main idea about a linear function. Both variables are to the first power. So nobody's squared or cubed or anything. So when I say that, then that means that rules this out, right? This is not linear, because it has this x squared, so that's non-linear. We'll study him later. You know, I said no exponents or anything. Now, all of a sudden, this is a square root. You know, at some point, we need to realize that actually square roots are exponents. That's sort of later chapter, but a square root can be written as x to the 1/2. It's a root. It's to the 1/2 power. The exponent is 1/2. I mean, I don't really want to teach you that now, but my point is it's not linear, right? It's a square root. It's kind of like an exponent in one sense. It is an exponent in one sense. Anyway, it's not linear. No. Now, my little definition of, everybody is to the first power actually doesn't really work right here. Everybody is to the first power, but he is not linear. He's not linear, sorry. So, because you have this x in the denominator. So, I guess I got to be careful about my definition. What's linear? Everybody's to the first power, and nobody's in the denominator. Nobody's in a square root or a cube root. So yeah, this is not linear because of that x in the denominator. Oh, by the way, yeah, okay. You know, again, this is, I guess I'm previewing exponents just a little. I didn't mean to do this, but I told you, you know, this is like an x to the 1/2, which then sort of fits my rule. Okay, it's got an exponent, it's not linear. You know, this is like x to the -1, which is also then sort of fits my rule. Okay, he's got an exponent, he's not linear. He's got an exponent other than 1. What about him?
Yes.
Yeah, okay, that's a linear one. Yes, okay, good. So this is what we study. Now he's in a different form than this one, but good. These two are linear, and you guys seem to kind of know that, and you should know that. And these other guys are non-linear. And one of your first 2 or 3 homework questions will kind of ask you that in 1.3. But otherwise, we quit debating these issues. We study lines. So we get rid of this and we study lines. Again, you know, last class we were plotting points. And I'll do that one more time. I'm not going to do it too long. But I'm going to plot some points. I'm going to plug in a -2, please. And I get -10, I think. I'm going to plug in a a 0, please. I get -6. I'm going to plug in a 1, and I get -4. I'll plug in a 3. I think I did that right, yeah, with the 1. Plug in a 3, and I get 0. That's kind of nice. So I'm just plotting points just for the heck of it. You know, I want to tell you something, though. I did just, and then I could graph this very easily. We did this the other day. You go from an equation to some points to a graph, and because it's a line, I really didn't need 4 points. You know, I was really just sort of plotting random points, but I want to point something out here. Point something out, sorry. When x is 0, I found this y value, and that's an important point. And you know, these are just a bunch of random points, but I stumbled onto a couple important points, like this one. When x is 0, this is y. What we found is this is the point when x is 0 and y is -6. This is the point that crosses the y-axis. The point that crosses the y-axis is a rather important point with a special name called the y-intercept. I actually sort of stumbled on another one. I didn't really intend to do this, but when y is a 0 and x is a number, when y is a 0 and x is a number, that's x equals 3 and y equals 0. That's that point on the x-axis. I mean, it's a true fact. Anytime that x is 0, you must be on the y-axis. Anytime that y is 0, you must be on the x-axis. And so this is an important point called the Xintercept. Anyway, there's a couple other points there, but if you connect the dots, you have this line. I didn't plot all of them. I plotted those two. I called your attention to those 2 important points. But the main thing about a line, and you know this, but I'm kind of reminding you about lines. Maybe you don't know it, but I'm doing this quickly. Is they have this thing called a slope, and the slope is represented with the letter M. The slope can be thought of as this phrase: rise over run. It is a ratio, and you saw what I just wrote, a ratio. It's a rate. There's a lot of words here. A lot of cool words here, actually. Sorry. I'm going to use another phrase here, or a word, rate of change. That's not a word. It's 3 words, or a phrase. Rate of change is a slope. It's a ratio. When I write the words rise over run, that's kind of a nice little catchphrase. Maybe you've heard that before. Maybe it makes no sense to you. I'll tell you what it is. The rise is how much the line rises as a ratio to how much it runs. So it's vertical change over horizontal change. Or you could say it's the change in y, that's the vertical change, over the change in x. And then I'm using this little Greek letter delta here. This is a Greek letter, delta, and in mathematics, when we use that, it means change in. Change in. So it's the change in x, the change in y over the change in x. Which finally leads me to this idea. Here we go. I'm connecting all these thoughts here about slope. If it's the change in y, that implies that there's 2 y's, kind of. How did y change? And so it's this. It's y with a subscript 2 minus y with a subscript 1. I don't think that's strange or difficult. I think it makes total sense from what the phrase is. The phrase is change in y. Well, then subtract a couple y's and you'll see how it changed. Over the change in x, which means you might have a couple x's. Look, we just put little subscripts to distinguish the x's. I think some students can't deal with the subscripts, but don't worry about it. It's 2 different x's, so we have little subscripts to distinguish the 2 different x's. But that's kind of the main formula you might think of for slope, but I used a lot of words here that all mean the same thing. They all mean the same thing. So I'm looking at this line. Maybe I could kind of see its slope. Maybe I can see how much it rises and how much it runs. Maybe you know something about the equation. I'll get there in a second. I've got plenty of points if I felt like doing a little slope formula here. If I felt like subtracting a couple y's and subtracting a couple x's, I could do that all day long over here. All day long. Watch this. If I calculate the slope using these 2 points, watch this. So here I go. I want to subtract the y's and subtract the x's. Sorry, what am I doing? I'm calculating the slope using these 2 points. Okay, I want to subtract a couple y's. I don't know, -6 minus -10. Can I subtract backwards like that? Got to be careful subtracting negative numbers. I'm going to take this 0. If I subtract that y minus that y, then I better take this 0 minus this x minus this x. 0 minus -2. That's a lot of work to see that the slope is 2. Maybe. I didn't leave myself a lot of room here. That's -6 plus 10. Oh, that's a 4. That's a positive 4. That's a positive 2. Yeah, cool. A positive 4 over 2 is 2. You know, and the slope is 2, right?
2 over 1.
Sure. The slope is 2, but any integer can be written as a fraction. The number 2 is always, can be considered 2 over 1. Seems kind of silly. The number 2 can be considered 2 over 1. When you're just counting numbers, you don't think about that too often, but when you're thinking about slope, you might want to, because it is this ratio. It is a ratio. So when you think of slope, you might want it to be a fraction. Anyway, we can say the slope is 2, but it might help us to realize that is 2 over 1, because it is a ratio. It sure is. Cool. Hey, so I did it using those 2 points. The truth is, if you really have a line and you really have linear data, then any 2 points should work. I mean, what makes it a line is that it has a consistent slope and it doesn't change. So I could have picked this point and this point, this point and this point, this point and this point. Any 2 points would have yielded the same slope if it's truly a line. I don't want to really do much of millions of slopes here, but if I did, any 2 points should have yielded a slope of 2. That's what makes it a line, really. That's what this line always goes up 2 and over 1. That's my rise over run. That's my ratio. This line has a slanting ability of go up 2 and over 1, up 2 and over 1, up 2 and over 1. That's what it does. That's what a slope is. Anyway, so I calculated it for you, grabbing a couple points. Look, here's another, here I am, I'm just going to see it. After I plotted these points, after I drew it, after I labeled this graph, I can see it so clear. Watch. How much do you rise? And how much do you run to get from here to here? You rise, how much do you rise? 6. How much do you run? 3. Thank you. It's a rise of 6, it's a rise of 3. I guess I really didn't do any subtraction that time. I just saw it. I just could see it and feel it. I'm rising 6, I'm running 3. That's the ratio, that's the slope. That's the rate of change, 2. What we learned is about this famous formula, y equals mx plus b, and now you've probably been waiting for me to say that, but when a line is in this form, you got your variables y and x, but this number in front of the x is the slope. We represent it with the letter m, and that's the slope. And that b is the y-intercept. And we call this is a very important formula you're probably familiar with. We call it the SlopeIntercept Formula of a line. I don't care too much about its name. If I refer to it, I call it y equals mx plus b form. But it's also SlopeIntercept form is its name, because in this form you see the slope and you see the y-intercept staring right at you. So back to my problem. You see it, right? I plotted points, I did all this work, but we already knew all that. If I knew that, I knew that already. the slope is 2, and the y-intercept is -6. And if you know that, then you don't really, then you don't plot a bunch of points. Here's what you do. Let's do this the real way here. If I give you this line in slope-intercept form, then to quickly draw a graph, this is what you do. You ready? This is how, and you guys know this, I think, but I'm showing you. Very quickly, you start at what's called the starting point, which is the y-intercept, I would say, which is what? 8. So, and that's on the y-axis at 8, somewhere. You start there. That's the one point you know, is that the y-intercept is 8. And then you do your slope, and your slope is what? What is your slope? It's 3/4. And it's this ratio of 3/4. And the 3 is the change in y, the 4 is the change in x, the 3 is the rise, the 4 is the run. So what I do is I start at this point and I go up 3 and over 4. And I can do that forever, up 3 over 4 if it's really a line. And I will, there you go. That's how you quickly draw a line. Given this equation, you saw that. I didn't make a chart and plot a bunch of points. I just used the knowledge of the slope-intercept form. If I know my slope and my y-intercept, I can draw a line so quickly. I need to know what that slope is, though. I need to know that it's this ratio of rise over run. That's the key. I mean, to me, that's key right there. You can interrupt me and ask me questions anytime. Are you doing okay? This is basic lines, right? Pretty basic. Let me tie it into a word problem real quick. In a word problem, I might say this. In 2010, my truck was worth $25,000. Nice rich kid's truck. But every year since then, it depreciates. It depreciates, which means it loses value. It depreciates. Every year it depreciates $3,800. So I just took a leap into word problems here just for a second. I mean, and if we're studying lines and linear functions, and they have a slope and a y-intercept, what that comes down to in word problems is kind of a starting number and a rate of change. Kind of an initial value and a rate of change. I mean, that maybe, you know, this is not a word problem. This is a math problem. And when it's a math problem, I still might use the phrase, it starts at 8, although starting at 8 doesn't really make sense. It goes, goes behind 8. I mean, it has a y-intercept of 8. And then it has this slope that causes me to go up 3 and over 4 up 3 and over 4 and draw a line. But you can sort of see maybe, but anyway, it goes, a line is infinite, so it goes on the left side of 8. So starting at 8 might be a little bit of a misnomer, a little bit of a bad phrasing, starting at 8, but it's not bad. I mean, if you know what I mean, the line keeps going. In a word problem, this really does start at, where does it start at? The value of my truck. 25,000. I'm going to draw a picture of this. And instead of X and Y, maybe I should label this the value of my truck, but that could be Y. It could be Y. And this could be X, would be, what would X be? What's going on?
Time.
Yes, time, and more specifically, how about years, right? Number of years. So this problem sort of starts at year 0. Well, what is year 0?
2010.
Yeah, 2010. But I want to label that year 0. Get used to that, you guys. When you're doing word problems, it might be 6 a.m. in the morning. Let's call that 0. It might be 2010. Let's call that year 0. The problem might start on September 1st. Let's call that day 0. You follow me? That's kind of the good way to construct a word problem. So 2010 we're calling year 0, and in year 0, what is the value of my truck? $25,000. Wow. What happens every year after that? What happens every year after that?
It depreciates $3,000.
So it loses value. It loses $3,800 worth of value. Right. So that means 1 year goes by. What just happened to my truck? It's lost some money, right? It lost. Let's see, what did it do? It went down 3,800 and over 1. Is that what it did?
Yeah.
Yep. What happens the next year? Down 3,800 over 1. Down 3,800 over 1. Now look at me. This is it. This is a beautiful linear equation, linear graph, linear word problem described with words. I see a starting point and I see a rate of change. When it's word problems, I tend to use that language. Listen to me. I tend to use the language starting value or initial value. But what does that correspond to in this equation? The initial value, the starting value is the y-intercept. Yeah. Starting value, initial value. You can use a lot of this language. So I might use that language instead of, it is the y-intercept. Okay, in word problem setting, though, I might use that language. And then instead of saying slope, another word for slope is this rate of change. And in word problems, it just kind of makes more sense to use that language, I think. So now, what's the rate of change? So I asked you, what's the y-intercept?
25,000.
What's the rate of change? 3,800, sort of. Let's write the equation for this. So I drew a picture, I did all this work. Really, what you ought to be able to do is read this and write a linear equation. You ought to read this and see the slope and the y-intercept and write an equation. And here it is, y equals 3,800x plus 25,000. The truth is, I just made a mistake. I wonder who knows it.
When the 25,000 be at the last? Minus.
Okay, I'm not sure what you said. You said something about the 25,000. What about it?
You wouldn't add 25,000.
Yeah, you would, because again, plug in a 0. Where do you want to be when this problem starts? Plug in a 0. You want to be at 25,000.
Okay.
See, the 25,000 is the starting value. But what I wrote is a rate of change that's going to grow 3,800 every year because I made a positive rate of change. Oops. The subtle word depreciates, and the concept that it's losing value I should have wrote negative. Thank you. It's subtle. This is negative. This is a negative rate of change, 3,800 every year. And then again, it's real common sense. Look, you plug in 1 year for X. You plug in 1 year, what happens? You lose 3,800. Plug in 2 years, you lose 7,600. Or plug in 3 years, you lose 3 of those. Plug in 4 years, you lose 4 of those things off of your initial price. Off of your initial price. Right. Yes, ma'am?
Is it okay if we write it other way? Or can I comparison?
Oh, what other way?
Like 25,000 minus 7,800.
I got you. I got you. Well, so she just said, so I'm trying to write it this way so you can see the mx plus b. So you can see the mx plus b. But in mathematics, addition is commutative, which means you can add things in any order. This answers your question. So, I mean, nobody ever write, and we all write mx plus b, but you could write b plus mx. And nobody does. But I see her point. With the word problem, you might consider, okay, you start at 25,000 and you lose 3,800 every x. I mean, it's logical to kind of think like that. But that is the same as this. You can add those two numbers like that, or you can add those two numbers like that. Right, it's the same. But now I have the y-intercept in front and the slope right there. It's okay. It's the same though. It is the same. All right. So, that's good. We're doing pretty good, I think. I mean, I don't know. So real quick, again, here's one more. Y equals negative 1.7x plus 8.6. I mean, can we quickly draw a quick graph of this? Tell me real quick, where should I start to graph it? At the y-axis, the y-intercept is staring right at me. It's 8.6. So I should go up here and call that 8.6, and I know that that's a point on the graph. And then what should I do? I should do my slope. And my slope is, what is my slope? Negative 1.7 is my slope. So I guess I should go down 1.7 and over 1. You can always consider these things over 1, right? You need to, really. So I can go down 1.7 and over 1. I can go down 1.7. Anyway, very roughly. There it is. I mean, that's how you quickly can draw a graph. You knowing the y-intercept and the slope, a starting point and a rate of change. I mean, I went down 1.7 and I just didn't obsess over it, okay? I went down 1.7 and I went over 1, you know. Same thing I did here. I went down 3,800 and over 1. Okay, good. Okay, so now what about this guy? Look, this guy, he's a line. We said he's a line. You see the x to the first. So he's a line, but he's not in this form. So we've been working on this form, y equals mx plus b. And we've been using this form. But he's not in this form. So what do you want to do? You want to put him in that form. Is that what y'all want to do? Yeah, I mean, I guess that's what I've been teaching you. If you have this form, you're good. You know the slope, you know the y-intercept. This is a good form to see and know how to use. So if it's not in that form, can you put it in that form? And what that form looks like to me is it's got y all by itself. You solve for y. So I guess that's what I need. I need to solve for y. Okay, you're suggesting I move the 3x over? Sometimes students make this mistake. When you move the 3x over, you lose this sign. So don't do that. It's still a negative 2y. But you just move the 3x over, so it's a negative 3x plus 6. This is algebra, solving for y. Move the 3x over. Now what? Divide by negative 2, and dividing by a negative 2 means you divide both of them. I'm dividing both of them by a negative 2. That leaves y all by itself. It's a positive 3/2. That's a positive 3/2 x. You could pick up a calculator and call it 1.5 if you want to. That's what it is. And this is negative 3. So now it's in this form. And you should probably know what to do. Real quick, I'm going to do it real quick. Here I go, real quick. The y-intercept is negative 3. Start there. The slope is up 3 over 2. Up 3 over 2. You with me, right? I mean, I hope it's not a mystery. Up 3 over 2. Up 3 over 2. Okay, cool, I'm done. Draw a line. There's other ways to do things. This is not the only way to do things. I mean, I was when it's in this form, I tend to do something different. You guys suggested we put it in this form, and I went with that. And of course, I've been teaching you about this form. I wanted to teach it. Yeah, I wanted to do that. But watch this. I got this different idea. Let's say we're starting over. Sometimes it's cool to plot points. I mean, maybe you didn't think that was cool. Make a chart and plot points. It's kind of tedious. But sometimes it's cool to plot just easy, important points like this. Watch this. If I do let x be 0, I mean, if I'm plugging in a 0 for x, what am I doing when I'm plugging in a 0 for x? I'm really finding the y-intercept is what I'm doing. When you plug in a 0 for x, you're finding the y-intercept. So I want to plot that. And watch how damn easy it is. Watch this. Watch me. To plug in a 0 for x, I go like this. I plugged in a 0 for x, and it's gone. I divide by -2, and what's y? I divide by -2, y is -3. I'm going to plug in a 0 for y. When I plug in a 0 for y, I think I'm finding the x-intercept. This is true all through this course. That's why I'm sort of trying to drive it home importantly now. All through this course, if you want x or y intercepts, this is what you do, kind of. So if I plug in a 0 for y, watch how I do that. And I divide by 3, what do I get? 2, x is 2. By the way, I already sort of saw that, but don't look down here. I plug in a 0 for y, I get a 2. So I just plotted a couple points. They weren't just random points, they were kind of important points. This is the x-intercept, the y-intercept, and the x-intercept. And with 2 points, I could draw a graph. The x-intercept is 2, the y-intercept is -3, and here's a picture of this graph without doing that, but whatever. I just have this habit. When it's in this form, I can easily throw in those zeros and easily get the answers. So I can easily plot these important points. So we just stumbled into this idea, which this point called the x-intercept. I mean, I guess I'm officially going to define it for you. You probably don't need this sentence, but here it goes. Of course, the x-intercept is the point where the graph crosses or touches the x-axis. That's what it is. That's what it is, okay? The x-intercept is the point where the graph touches or crosses the x-axis. You know that, I guess. How you always find an x-intercept, always, and this is, again, we'll get higher level functions we'll learn about all semester. You need this thought all semester. If you want to find an x-intercept, you let y equal 0, because that's true. When you're on the x-axis, y is 0. You let y equal 0 and you solve for x. That's how you always find the x-intercept. For the y-intercept, you know what it is. It's the point where the graph crosses the y-axis. Is that okay with you? But in order to find it, you let x equal 0 and you solve for y. That's how you find it, if you ever want to find it. I guess maybe we mislead you at first because we give you this magic formula where we say, oh look, if you look at this magic formula, that number is always the y-intercept. Well, yeah, but it's really logical. If you plug in a 0 for x, what do you get? You plug in a 0 for x, you get that number. Maybe that's why that number is the y-intercept. When you plug in a 0 for x, you get that number. So this is good not just for chapter 1, but for the rest of your life. Well, your mathematical life. Yeah. Hey, just to tie this back into that word problem over there, watch this, look at this question. When is my truck worth nothing? I don't know. You could look at the picture again. You could think about it. You could do this without my lecture. You could just logically figure it out yourself. But I'm trying to use the language of lines and slopes and stuff. And anyway, when is it worth nothing? This is the value of my truck here. It's losing $3,800 every year. At some point, look, it's worth nothing, right? It's worth nothing. I guess that's the x-intercept. And I guess when I say when I use the question when, that usually means I'm looking for a time. And x-axis is time. The x-axis is the number of years. So, yeah, I think you can interpret this word problem. Again, I'm trying to interpret. You read the word problem and you think mathematically, this is the x-intercept is what this is. And how do I find an x-intercept? I let y equal 0. But logically from the word problem, forget that a second. Logically from the word problem, when is it worth nothing? It's worth nothing when the value y, the value is 0, right? Right, so there's a couple of good reasons why. You plug in a 0 for y and you try to solve. You plug in a 0 for y and you try to solve for x. Hey, notice it's in this form. It was in this y equals mx plus b form. So when you plug in a 0 for y, you got a little algebra to do. You got to move the b over. You got to divide. You got to do a little bit of algebra here. I'm gonna move the 3800x over here. 3800x equals 25,000. I'm gonna divide by 3800. I'm gonna pick up a calculator, please. Divide by 3800 and maybe round it to tenths of a year or something like that. What did you say? Is she right? Well, you need a calculator. I mean, it's either, right, I would call it 6.6 if what you said is true. I think you're probably close. Yeah, you're probably right. Did you do it? 25,000 divided by 3,800. Yeah, she's right. 6.57, blah, 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 blah. It's right. Some kind of strange fraction, but it's a word problem. It's okay for us to round this off and call it 6.6 years. Wow, it's worth nothing in 6.6 years? That's not good. That's not good. You know, when I make up these problems, sometimes they're reasonable, sometimes they're not reasonable. They're just examples of word problems, and they might not be realistic in any way. This is semi-realistic in the sense that, you know, a truck could be worth this much, and it could be losing value of this much. They do depreciate quickly. The truth is, though, and this will be about 2 months down the road, they probably don't depreciate linearly, okay? They probably don't depreciate in a line. What they tend to do is depreciate along a curve. Again, this is just a preview of chapter 5. They probably depreciate along a curve like this. So they depreciate a lot at first, but it's not linear. It's not the same amount every year. I mean, 6 or 7 years down the road, it's not 3,800 every year. It's depreciating less as time goes on. So, anyway, what did I just do? I made up a word problem and then shot it down. Sorry, I didn't mean to shoot it down. It's okay. It's an estimate of linear depreciation. In real life, might not be that accurate. Let's do, here's a couple of strange lines. Now, I'll tell you what, let's talk about this idea of slope here just a second. So here's kind of a strange line right here, y equals x. I think I want to draw this guy. Again, this is your buddy. To me, you need this formula. You need it in your head. I use it a lot. Can you please tell me how to start? What's the y-intercept? And when there's no number there, what is it?
0.
It's 0. So that means it goes through the origin. But sometimes when there's no number there, it confuses students. But yeah, it's 0. That's okay. It's 0. And then you say, well, there's no number there. But wait a minute. There is a number there. What is it?
1.
It's a 1. So the slope is 1. So if the slope is 1, then that means it goes up 1 and over 1, and that would be, this is a pretty famous line. It goes up 1 over 1, up 1 over 1. It's a perfect diagonal here. I don't really want to get into angles, but that's a 45-degree angle. It cuts this 90-degree angle in half is what it does. It's a 45-degree angle on either side, and it's this perfect diagonal line. And it has a slope of 1. Here's what I'm trying to do at this moment. I'm trying to make you think about the value of slope. So when you have a slope of 1, there you are, a perfect diagonal. Guess what? A slope less than 1, like 0.9 or 0.8 or 1/5 or 3/4 or 2/3, a slope less than 1 will be less steep. Are you following me? So any of these a slope less than 1, there's all kinds of lines with what, a shallow slope less than 1. A steep slope bigger than 1 would be like a slope of 2 or a slope of 4 or a slope of 10 or a slope of 20. That's steep. And that's over here. That lives over here. These are steep slopes. I mean, it goes up 10 and over 1. That's steep, right? Right. But they're all positive slopes. When they slant this way, they're all positive slopes. Kind of having 1 in the middle there. Less than 1 and more than 1. Hey, watch this. Less than 1, less than 1, less than 1. What if you get really, really shallow? I mean, what would be this slope? Like maybe 1/100th? You know what I mean? Real shallow slope. What if it becomes completely flat? Well, just above flat, it was a teeny little fraction. So when it does get completely flat, 0. That's a slope of 0. And it rises 0 and runs. Well, it actually runs whatever it wants to run. Look at it. How much does this, to go from this point to this point, it rises nothing, but it runs 6 or 7 or 8 or whatever you want to say. But its slope is 0. And it's a horizontal line. Hang on, watch this. What did we say about this slope? That 10, 20 would be steep. What about 100? You go up 100 and over 1. That would be steep as hell. What about 1,000? It goes up 1,000 and over 1. Super steep. In fact, it's so damn steep it would look like it's vertical. The truth is, once it's vertical, its slope is bigger than 1,000, bigger than 1,000,000, bigger than 10 billion. Guess what it is? Infinity. But we don't say that in this class. That's calculus. Hang on. When the slope gets super steep, we say it's undefined, actually. We call it undefined. When it's, wait a minute, super steep, I mean, when it gets vertical, it's called undefined. When the slope gets vertical, I'm trying to make you think that it's huge is what it is. It approaches infinity. But once it's vertical, it's called undefined. We call it undefined. The slope of a vertical line is undefined. So there's some weird things. There's normal slopes, and then there's a couple strange ones. A horizontal line has a slope of 0. A vertical line has a slope that's undefined. The problem with those guys is they kind of don't, those concepts don't really fit this formula all that well. See, here's a line with a slope of 0. You ready? It's called y equals 6. Y equals 6 is up on the y-axis. I guess you could, if you are trying to fit this formula, what would you call that 6? If you're trying to fit this formula, what would you call that 6? The y-intercept, maybe, yeah. And then, look, what would you call the number in front of x? Well, there ain't no x, so that m must be 0. So this is a horizontal line at y equals 6. Here, I'm going to write some more. That's its equation. That's its picture. I'm going to write the word horizontal, and then I want to say something about its slope. What is its slope? What is its slope? What is it? Thank you. I just couldn't hear you too well. Thank you. Other people can chip in if they want, but thank you. Yeah, the slope is 0. He's a horizontal line. I mean, those words, those thoughts should go together now. These are concepts that are tied together. A slope of 0, a horizontal line, a picture like that. And then the equation is just y equals a number. Hey, what if it was this horizontal line going through 2? What would his equation be? Y equals 2. What if he's down here and he goes through -10? What's his equation? Y equals -10. It's an easy, it almost doesn't fit the formula, but it sort of does. If the slope is 0, you just get y equals a number is what you get. Y equals a number. All right, so those thoughts need to go together. Check this one out. Check this out. Over here at 3, I'm going to draw a vertical line. His name is x equals 3. He does really, don't try to even make his, or you can try for a second, but how does that equation fit this formula? There is no y. There really is no b. Look at the picture. Is there any y-intercept? If there's a vertical line, it ain't gonna, no, there won't be a y-intercept. There's really no y-intercept. There's really no slope. Don't even try to make, he doesn't fit this formula. He's a weird little dude. He's a vertical line. He looks vertical. I'm going to write the word vertical. He's a vertical line. His equation is very simple. X equals a number. What if he was over here at 5? X equals 5. What if he was over here at -10? X equals -10. That's his equation. That's his picture. He's a vertical line. And if he's a vertical line, what's his slope? Undefined. And maybe that's why he doesn't fit the formula. His slope's undefined, so you can't really plug the word undefined. The formula doesn't really work. Also, he's a little weird because he's a line. I guess he falls in the category of lines, but he's so weird because he's a vertical line. Guess what? Remember our discussion last week? Is he a function? Is he a function? Does he pass the vertical line test? If you drew a vertical line, do you only touch it once? No. If you happen to draw this vertical line, you touch it 1,000,000 times. He totally fails the vertical line test. Totally fails the vertical line test. Okay. So he's a weird little, he's a line. He's a special little vertical line, whatever. He ain't a function. He doesn't fit this formula. He's worth mentioning. I would kind of consider both these guys kind of strange, and I would kind of just memorize them sort of separately. This scenario here goes in one brain cell. This goes in another brain cell. And you got your whole study of lines, other lines that slant and slope. This guy has a slope of 0. You know, I drew this picture. All these lines have positive slopes. The slope is positive. And then when it got very shallow and got like this, you know, it was horizontal, the slope was 0. If it goes below that and it's a line that slants this way, these are all slopes that are negative. The rise over the run is negative. Maybe the rise is negative. You're falling and running. You're falling and running. Now, you saw me do a couple of those today. I had a negative slope a couple of times. A slope of 0, and then positive slopes. And then if it gets too steep, it's just this undefined slope. So I'm sort of doing concepts here. I'm not really doing problems here. But I've done a lot of problems. I think I'm going to do something a little different here now. I think I'm going to ease on into 1.4. And I'm going to have more to say about 1.4, but we got 15 minutes left. I might use some of that time here and just ease you into 1.4. Let me say this, though. So in chapter 1 with lines, all of a sudden we do have some formulas we need to memorize, and I wrote them down, but just to summarize them, you know, this slope formula is probably useful. So if you have a couple of points, if you want to subtract the y's and the x's, you can get the slope of a line if you have points. And then we learned how this formula is pretty useful. So there's a couple different formulas for lines. I got another one though. See what I want to do, what happens in 1.4, so what I was doing to you in 1.3 is I was kind of giving you the equation of a line and asking you stuff about it. What's the y-intercept? What's the slope? Blah, blah, blah. Let's sketch a graph. Let's do this, da, da, da. Okay. What happens in 1.4 is it's kind of backwards. I'm going to tell you some stuff about the line, and then you got to get the equation. You got to get the equation. So that's different. Again, two kinds of problems. I give you the equation and ask you some stuff, or I give you some stuff and ask you to find the equation. I don't know, those are two good questions that we kind of do all semester, actually. But here we are with lines. So the question is, find the equation of the line. That's the typical question. Find the equation of the line, and I can give you a couple of things. I think I'll give you this. That I'm going to say it has a slope of 3/5 and a y-intercept, this is too boring actually, of -3. So guess what I did? This is way too easy. Maybe you realize how easy this is. I'm so sorry. I'll step it up here in a second. What did I do? I said find the equation. I gave you the slope. I gave you the y-intercept. If you have the slope and the y-intercept, you're done? Aren't you done? Finished? Home free? If you use this formula. Right. You follow me? Yeah. So we're done. What's the equation? The question is, what's the equation of the line? I gave you a slope and a y-intercept. Here you go. I don't even care. It doesn't say graph it. It just says, okay, there, I guess the equation is 3/5 x minus 3. I'm done. Finished. Go take a nap? No, wait a minute. All right, let's step it up a little bit. Maybe you don't know the y-intercept. Maybe you don't know the slope. Maybe you don't know the slope of the y-intercept. Maybe it's this question. Watch this one. This is the best question. Find the equation of the line, and I give you, watch this, that goes through, I'm going to write that goes through 8, -1, and 4, 7. So now I've given you 2 points. I want the equation of the line, and I've given you 2 points. I want the equation of the line, and I've given you 2 points. I want the equation of the line. So my brain is thinking like this. Man, if I want the equation of the line, I sure wish I had the slope. I don't have the slope. But they gave me 2 points. If they gave you 2 points, you can always find the slope, right, you guys? So step 1, find the slope. Maybe this problem is 2 or 3 steps. Step 1, let's find the slope. The slope is subtract the y's over subtract the x's. We haven't really practiced this much. You will when you do some of this homework. Listen, all you got to do is subtract 2 y's. 7 minus -1 over 4 minus 8. Did I do that okay? I mean, if you do that y minus that y, then you better do that x minus that x. You got to stay consistent in your subtraction. So I did that y minus that y. I did that x minus that x. Truth is, I could have done it the other way, but just stay consistent. What is that? 8 over -4, I think. That is -2. Cool. I got his slope. Now, if I had his slope and his y-intercept, I'd be done. You know, that's what happened in the last easy problem. I don't have his y-intercept. I got his slope, and I got a couple of points, but I don't have those points are not his y-intercept. So now I got a different formula for you. Here's one more line formula is this. It's called y minus y1 equals the slope times x minus x1. This is called the point slope formula. This is a good formula to use when someone says, find the equation of a line. When someone says, find the equation, and this is usually what you're using. When someone says, find the equation of the line, you're usually using this. And in order to use this, what do you need? You need a slope and a point, any old point. And you plug that point in for the x1 and the y1. You leave the y and the x variables, of course, because your line has to have variables in it. Your equation has to have variables in it. But you need a slope, and you need any old damn point. Hang on a second. What do you need for this problem? You need a slope and, very specifically, the y-intercept. But this works good when you have the slope and not the y-intercept, some other point. So here I go. Step one, we found the slope. Now I'm going to use that formula. I can use that point or that point. I think I'll use this point. And here I go. Y minus the y value of the point, 7, equals the slope, I'm doing this formula, times x minus the x value of that point. I did my slope and my point. I could have done that point. It would have worked. It would have worked. But there I am. That's the equation of my line. In a way, that's the equation of my line. I don't want to leave it there, though. I want to distribute and clean it up. I probably want to put it in this form. I used this form, but I want to clean it up and leave it in this form as my answer. So let me do a little algebra here. Distribute the -2. Add 7. And y equals -2x plus 15. That's the equation of the line they were describing. That's pretty powerful, you guys. You can take the data, someone gave you the data, and you found the equation. Step 1, find the slope. Step 2, use this point slope formula. You all right? Any questions? There's other versions of this question. We can step this up a little bit, like you saw. Here's one version that was real easy. Given the slope and the y-intercept, I'm done. Given 2 points, I got a little work to do. There's other ones about being parallel or perpendicular to another line, which means I should bring up those concepts of parallel and perpendicular. But I don't think I will today. So I think I'm stopping now. I'm sort of stopping in the middle or beginning of 1.4. I feel like you can handle 1.3, and I think Thursday I'll just flip on the computer if hopefully the computer's working, and maybe we'll do a little homework together. If you have some questions, maybe you can jot down 1.1 number 12 or 1.2 number 6, or whatever's been bothering you, I can help you with Thursday. Yes, ma'am. The math, yeah, I heard that the My Math Lab system was having some issues the last couple days. Yep, I heard that. Everybody's been okay? I mean, I've accessed it. Maybe not too many people have accessed it too much yet.
I did mine. Mine says session expired, but I just put it on the access code.
Oh, okay. Yeah. I don't know what that means. I don't know either. You put in a new access code, and you use my course ID.
Yeah.
Right. So you should get into my course. Well, keep trying. Yeah, keep trying. And if there really is technical issues, I might not be the guy with the answers. If there really is technical issues, you might need to contact that company, Pearson. You might find a phone number or what'd you do, buy an access code, or you went online and bought one?
No, I bought one.
Yeah. So there might be some information how to get some help, some technical help, if you have to. But maybe you don't need to. I don't know. Maybe it's. Yeah. Okay. We'll keep trying. Yeah. All right. Thank you guys. I'll see you Thursday.